What's going on, everyone? You're back with your boy Jono for another quick math lesson. Today we're going to have a look at displacement time graphs again, but this time we're specifically looking at ones that go below zero. This is something that students sometimes find a little bit confusing because it doesn't look like a normal graph, but I guarantee you've got all the skills already in order to smash this topic. So the major thing we're looking at this time is when we've got a negative displacement. That doesn't mean someone's going backwards or anything like that. It just means they've stopped moving in the positive direction, the direction that was given, and they're now moving the other way. They could be going the same speed, the same velocity, all of that stuff. They're just not going in that same positive direction that was outlined at the very start. So we're actually going to look at an Ironman competition just so we can see someone's place during a race and see how that relates to the starting point. This is a really good thing to look at because we've got a swim, a bike, and a run that are all going to be at different speeds naturally, and we're just going to make some assumptions about how fast an athlete was going. An Ironman is just a 4K swim, 180K ride, and then just a marathon to finish off. Pretty easy, and we're going to have a look at how that can impact someone's speed or velocity. So the big point before we get into our graph is that the direction matters. If you've got a negative gradient, that does not mean that you're going slower or you're going backwards. All it means is that you've turned around and you're going back home. You're going the opposite direction. So just remember, negative gradient does not mean backwards or smaller, just means in a different way. So big shout out to Cody here. He's finished an Ironman and we're just going to look at their displacement during the race. So we've broken this into three sections. The red section here is the swim. The blue section here is the ride, and the black section at the end is the run. One thing that we just have to take note of before we get started is that this graph starts at zero and ends at zero. So what that means is that we start at a position, our starting point, and we're going to finish at the exact same position. So our whole displacement for the entire race is just zero. And as always, anytime we're looking at a graph, we've got to be 100% on top of the units. So this one we're looking at displacement east. That is the positive direction, east, and that's going to be in kilometers. And we're looking at this over a number of hours. So Cody here finished in 12 hours, just a casual 12-hour stroll, and that's something that we're going to use to find out our speed and velocity for the entire race. So there are going to be two types of questions you could be asked. Number one is going to be, tell me about the graph. Tell me about what's happening at certain times. And the other type is going to be more mathematical. Some of these tell me about the graph questions will look something like this. Which one's fastest and which one's slowest? When we're looking for total velocity or how fast you're going at any one time, all we're really looking for is the steepness of the gradient. The steeper the line, the faster you're moving. So for the bike, because that's incredibly steep compared to everything else, we can immediately, without having to do any maths, work out that that's when this athlete was moving at their fastest. Because that swim leg is really flat, the gradient there is quite flat, that's when we're going the slowest. And this probably just makes sense intuitively. On a bike, you can go way faster than if you're swimming. Swimming's way harder. Another type of analyze question could be something like this. When were you furthest away from home? In the easterly direction. All we've got to do here is make sure that we're looking up the graph, because that's where east is, and just go across to the highest dot point. This is 30 kilometers across, so our furthest displacement is 30 kilometers east. When we analyze this, we've got to look at what these turning points are. What's happening at 6 hours? So what's really important here is that just because it's going downhill now does not mean that Cody's going slower. All that's happened here is they've gotten to a cone and they're turning around. They're starting to ride back home. This makes sense for a lot of like athletic events when we've got a loop. All that's happening is we've got to the end of the track and we've got to get back home. So this length of track would probably be 30 kilometers east and then 30 kilometers west, with a point in the middle being the start and finish. And because the gradients are the same on both sides, the positive gradient and the negative gradient are both saying 30 kilometers per hour, we know that the speed is the exact same. So even though it's negative, we're going the same speed, just in a different direction. So here we're going to get into some more mathematical calculations where we've got to get the data from the graph and then turn it into a mathematical formula to get an answer. So for this one, we're looking for how fast or what's the total speed of the athlete during the run. So the run is actually 42 kilometers. That's a marathon. On our graph, we've just got the 40, so that's what we're going to use. So we can see that it's going to take 5 hours for the athlete to finish. Cody took 5 hours to finish the marathon part. But because it's only 40 kilometers, all we need to write down is the 40 kilometers divided by the 5 hours. 40 divided by 5 is 8 kilometers per hour. We need to make sure that we've got the units afterwards, otherwise you will lose a mark. And because we're just talking about speed, we don't need a direction. And if you think that 8 kilometers per hour is pretty slow going, if you've already ridden your bike for 6 hours and swum for an hour, I reckon 8 kilometers is pretty quick. This question here is trying to determine whether or not you know the difference between distance and displacement. What's the velocity of the athlete for this run? Because velocity is looking at the total displacement overall, because we start and finish at the same spot, our displacement is just 0 kilometers. That means that our velocity is 0 kilometers per hour in no direction. Velocity questions are always way easier to work out, especially when they're like this, but we just need to make sure it's just the start and end point that determine our displacement. Now a little bit more mathematical, we're looking for the velocity of the first half of the run. So this is just where we go from our start position and we're going 20 kilometers west because it's in the opposite direction of east. So because we know that we've gone 20 kilometers in 2.5 hours, we just have to do 20 divided by 2.5 in our calculator, which is equal to 8 kilometers per hour. The same as our overall speed. But because we're talking about velocity, you have to have a direction. Just the 8 kilometers is not enough to get you the mark. For this one, we're going 8 kilometers per hour west, and that bit is really important. The units always will get you a mark. Finally, we want to find out what the average speed of Cody was for the entire journey in kilometers per hour. So what we've got to do is find his total distance. The swim was 4Ks, the ride was 180, and the run here was 40. So he's traveled 224 kilometers in 12 hours, which is pretty good going. All we've got to do to find the answer is throw this into the calculator, which is equal to 18.67 kilometers per hour. This makes sense. We're probably going slower in our swim and slower in our run, but because we're going at 30 k's per hour during the bike, that's really pushing up how fast we're going for the entire race. So if you just think about moving 18 kilometers for an hour for a whole day, for 12 hours, you can see how pretty impressive these Ironmen are. Just to put this in another perspective, we're going to find out the average speed for the whole race in meters per second. How many meters did they move every single second? So in order to get this right, we've got to change our kilometers into meters and our hours into seconds. So what we have to do is multiply our 224 by 1,000 in order to get our meters. Converting hours to seconds is a little bit harder. We have 12 hours and we're multiplying that by 60. But that's only giving us our minutes, so we have to multiply it by 60 again. So all we've got to chuck into our calculator is 224,000. That's how many meters were done during this day event. And we've got to divide that by 43,200. That's how many seconds it was in total. This is just equal to 5.19 meters per second. The big takeaway for this lesson is please just make sure that you understand that the negative gradient doesn't mean slower, it's only talking about the direction. We can even go into the negatives with displacement. That doesn't mean that distance doesn't exist or whatever. It just means you're going in the other direction than was specified at the very start. This is why it's so important to assign a positive and negative value to a direction at the start of a question, and just make sure you're looking at that units as you get started. Thanks so much for watching this lesson, and I'll see you later.